Hello and welcome everyone to the infrastructure breakout session. Today we're going to have three fascinating and innovative presentations for you. We're going to be holding questions to the end of the webinar, so if you have anything you'd like to ask or comment on, please use the question and answer tab to do so. Without further ado, we will start our first presentation entitled Achieving Resilient and Smart Concrete Bridges by Mapping Strains and Cracks Using Distributed Fiber Optic Sensors by Kaan. Xiao is a PhD candidate at the Department of Civil and Environmental Ocean Engineering of Stevens Institute of Technology. Xiao currently works as the Lab Operation Manager and Research Assistant of the Smart Infrastructure Laboratory in Stevens. In recent years, Xiao has won the Best Poster Award at the 2019 Research Showcase and was also awarded the Excellence in Doctoral Fellowship, Provost Doctoral Fellowship, and Graduate Teaching Assistant Fellowship by Stevens Institute of Technology. He is currently working on the USDOT-funded research on using distributed fiber optic sensor network for real-time monitoring of pipeline interactive anomalies. Xiao?
Hello. Hello. Okay. Can you hear me?
I can hear you.
Okay. Let me share my screen. Okay. Can you see my screen?
We can.
Okay. Hello, everyone. This is Kaan, a PhD candidate of Stevens Institute of Technology, and I am now working with Dr. Bao at the Smart Infrastructure Laboratory in Stevens. Today, my topic is achieving resilient and smart concrete bridges by mapping strains and cracks by using distributed fiber optic sensors. Before the presentation, I'd like to introduce our group firstly. The newly upgraded Smart Infrastructure Lab is aside the Hudson River and facing the midtown of Manhattan. The lab is used for large-scale structure testing, which equipped with MTS high-capacity actuator and advanced instruments such as optical camera, fiber optic sensors, and so on. We also develop smart robots for bridge condition assessment. We also have an advanced concrete technology lab. We have 6 mixture for the mixing and the universal machines and the environmental chambers for the mechanical temperature and the humidity testing. We also equipped with instruments for the multi-scale characterization of the concrete, such as the isothermal colorimeters, TGA, MIT, and so on. We strongly welcome the inquiry into the research collaborations and the education opportunities. As we all know, bridges are subjected to cracks caused by different reasons, such as shrinkage, temperature gradients, overloading, and other unexpected effects, which can compromise the loading capacity and the durability of bridges. Based on this background, this study developed a method to measure and visualize strains and cracks in concrete using the distributed fiber optic sensors based on the optical frequency domain reflectometry technology, which is OFDR. We aim to improve the resilience of bridges by providing detailed information of the condition and enabling timely repair of bridges. The contents of this presentation are shown below, including existing methods for monitoring cracks, challenges of monitoring cracks, proposed technology, experimental testing and the results, and then the conclusion. The first type of existing methods for crack monitoring is point strain sensors, including strain gauge, vibrate wear gauge, fiberglass gauging sensors. However, this type of sensors is difficult to capture cracks due to the short gauge lengths, and the location of cracks are hard to predict, so many sensors must be deployed, which is unrealistic in many cases. The second type of methods is surface inspection methods, such as photogrammetry, laser scanning, and computer vision. However, this type of methods can only detect and quantify surface cracks, but cannot detect invisible cracks. Besides, the accuracy of these methods is subjected to many variables. Another type of methods is non-destructive technologies such as cold wave interferometry, ultrasonic testing, acoustic emission, which are based on the electromagnetic waves or mechanical waves. However, the spatial resolution of this type of methods is limited. Also, the accuracy is subject to many variables, such as EMI, humidity, and so on. Compared with existing methods, fiber optic sensors are a type of promising method for monitoring cracks, which can detect and locate cracks. In addition, the widening of the cracks is traced by the increase of the peaks. Fiber optic sensors use optical fiber for the measurement. Normally, a telecommunication-grade single-mode optical fiber consists of core, cladding, and coatings. The principle of fiber optic sensor is through total internal reflection of the guided light at the core and cladding interface. Fiber optic sensors can be categorized into three groups: the grating-based sensors, interferometer sensors, and the distributed sensors. Among them, the grating-based sensors and the interferometer sensors are point sensors. Although they can be integrated as a quasi-distributed sensors, there is always a spacing between the point sensors, so many sensors must be deployed. Compared with them, distributed sensors have a unique advantage of utilizing a single fused silica fiber as both the transmission line and the sensor with thousands of sensing points. In addition, distributed fiber optic sensors are immune to the electromagnetic interference and have high accuracy, small size, desired physical and chemical stability. With above attractive features, distributed fiber optic sensors have been applied to measure strain distribution in various structures. For the strain measurement, distributed fiber optic sensors can be categorized into two groups: the Brilliant scattering-based sensors and the relay scattering-based sensors. Compared with relay scattering, the Brilliant scattering features long measure distance, but the limited spatial resolution. For example, Brilliant scattering technology such as Brilliant optical time domain analysis has a spatial resolution of tens of centimeters, which leads to uncertainty in detection, location, and quantification of the cracks. Accurate measurement of crack width require higher spatial resolution. To enhance the spatial resolution, relay scattering-based distributed sensing technology such as OFDR are proposed and achieve the sub-millimeter spatial resolution at large strain range. With the fine spatial resolution, fine strain distribution and cracks can be precisely located and quantified. Besides, the OFDR also has the advantages of high sensitivity, high stability, long durability, and the capability of quantifying the crack width. A bending test is used to simulate bridges in the experiment programs. The two beams have the same dimension as shown in the following pictures. Each beam was instrumented with two distributed sensors, including one sensor embedded in concrete and one sensor attached on the surface. To capture the development of cracks, the sensor run along the beam back and forth, forming the four different passes at the different heads of beams. The table lists two different HPFRC mixtures designed as HPFRC1 and HPFRC2, which adopt to fabricate beam 1 and beam 2 respectively. Basically, HPFRC1 was reinforced with PP fibers, and HPFRC2 has both PP fibers and steel fibers. The figure below shows the stress strain curves for the steel bars and the CFRP tendons. The slide shows the concrete casting and the finishing of the castings casting surface. The beams has coarse aggregate and low flowability. An electric vibrator was used to consolidate the concrete. After the concrete placement, the beams was cured in air at 25 degrees C with a relative humidity of 50%. The distributed sensors embedded in concrete survived through the concrete casting process. After the beam were cured for 28 days, they are tested on 4-point bending test setup, as shown in this figure. The bending test is conducted under force control until the beam failure. The applied load was recorded by 2 load cells, and the beam deformation was measured using 5 linear variable differential short translation formula, which is LVDTs. Cracks in the beams were examined through the visual inspection using the digital crack scopes. Once the crack was found, the crack scope was used to take pictures of the cracks, and the pictures were used to quantify the crack width. With the increase of the applied load, cracks were generated in the beams. The 2 beams show the similar cracking process, thus only the observation of beam 1 are elaborated. A total of 16 cracks were observed. The first crack occurred near the midspan, and when the load was increasing, the crack was generated away from the midspan. This slide shows the relationship between the applied load and the midspan deflection of the beams. The curves of 2 beams show the similar trends. The load was linear increased until point P1, where the first crack was observed by the crack scope near the midspan of the beam, and the midspan deflection was increased from P1 to P2. The slope of the load deflection curve was reduced because more cracks were generated. When the midspan deflection was increased from P2 to P3, the slope was gradually reduced to 0. Eventually, the beam failed in the fracture. Before the concrete cracking, the mechanical analysis of the beam can be conducted to analyze the midspan deflection, the moment diagram, and the strain distributions. The strain distributions measured from the distributed sensors also plotted and compared against the theoretical results. When beam 1 was subjected to the load of P equals to 6.4 kilonewton, the strain distribution measured from the distributed sensors are in good agreement with the theoretical results. As the applied load was increased, the cracks were initiated in the concrete. In this study, since the distributed sensors were deployed along the beams, cracks in the concrete passed through the distributed sensors and caused the strain peaks in the strain distribution measured from the sensor. It should be noticed that the strain distribution measured from the 5 different passes of the distributed sensor in beam 1, when the applied load was 19.6 kilonewton. However, the cracks detected by the distributed sensors were too narrow to be visually observed using the crack scope until the load was increased to 34.7 kilonewton. This result shows the high sensitivity of the distributed sensors. With the increase of the load, new peaks appear in the strain distribution, meaning that the new cracks are generated in the concrete. The magnitude of peaks are increased, means that the width of the cracks are increased. The distributed sensors not only detect the cracks from C1 to C16 that were found through the visual inspection, but also detect micro cracks from the C17 to C21 that are not found using the crack scope. These results also show the high sensitivity of distributed sensors. With the location of the distributed sensors in the concrete beams, the distance along the distributed sensor is correlated with the position of the beam. Once the correlation is established, the strain distribution measured from the distributed sensor can be replotted using the coordinate system of the beam. The different passes of the distributed sensor show the variation of the strains and cracks over the depth and the width of the beams, and each pass shows a variation of the strains and cracks along the length of the beam as shown in this figure. The location of the cracks that are identified from the strain distribution measured from the sensor were in good agreement with the crack that visual observed. The results of strain distribution can be replotted in the form of contour to visualize strains and cracks. The area of concrete subjected to the high strain are shown in the red color, which indicates that this area have a severe cracks. In this study, the crack width is calculated by the integration of the strain corresponding to each peak in the concrete, and compared against the crack width measured from the crack scope. The results from the distributed sensors and the crack scope agree very well with each other, indicate that the crack width can be measured by the distributed fiber optic sensors. Based on the above investigations, the following conclusions can be drawn. Strains and crack distributions were measured from distributed sensors. The initiation and the development of cracks were monitored in real time. The distributed sensors are capable of detecting, locating, and quantifying cracks earlier than the visual inspection of the cracks. The development method for the installation of distributed sensors enabled the sensor to survive throughout the concrete casting and beam testing process. It is promising to prove the resilience of concrete bridges by providing detailed and precise information of the health condition for time-effective repair for the bridges. This research was funded by the U.S. Department of Transportation, NJDOT, and the Stevens Institute of Technology. We would like to acknowledge Rutgers for the assistance in casting and the loading of the beam. Thank you for your listening.
Thank you so much, Xiao. It was a wonderful presentation. If anyone has some questions, please ask them now in the question and answer section. We do have one question that came in during the presentation. Do you think that different kinds of aggregate and flowability of the concrete will make it more difficult to install the sensors?
Yes, of course. When the flowability is low, actually the sensors is embedded in concrete, is installed in the steel frames. Mm-hmm. And when the flowability is low, and which make it more difficult to install the sensors.
We have another question about the total cost of using fiber optic as opposed to other methods. Was it less expensive?
Actually, for the optical fiber itself, it's very cheap. It's only about maybe $1 per 2 meters, like this. But for the instrument itself, it's a little bit expensive.
Okay, I believe that's all the questions we have here right now.
Okay.
I don't see anything else coming in. Thank you so much for your presentation, Xiao.
Thank you so much. Okay.
We're going to move along to our second presentation. It'll be Dr. Sougata Roy. He's an associate research professor of civil and environmental engineering at Rutgers University and affiliated faculty of the Center for Advanced Infrastructure and Transportation. Dr. Roy has more than 22 years of experience in experimental and computational research in academia and industry on bridge and highway infrastructure, including development and assessment of innovative structural systems and connections, renewal of damaged and deteriorated systems and extending service life, evaluation of innovative material and technology, and fabrication processes. Dr. Roy's research has led to the development of AASHTO specifications, numerous technical and research reports, and has authored many journal and conference papers. Dr. Roy?
Thank you, Omid, for the kind introduction, and welcome everyone for this session. I think you are being able to see my screen. Is that okay?
Yes, we can see it.
Okay. So let me go to the presentation mode. So today we are going to talk about, excuse me, the innovative metal deck for efficient infrastructure. So the topic that I'm going to address is the challenges that the US infrastructure or the bridge infrastructure faces, mostly due to the damages that we see, particularly in the Northeast or in the colder environment, where elements of weather like freeze-thaw cycles, rain, and other elements, and then winter maintenance like road salt that is used for keeping the roads operable during winter months, and then finally live loading, that's aberration due to heavy live load. There are a lot of traffic, heavy loaded trucks and heavy live load in this Northeast region, particularly New Jersey, New York, in this area. Those all kind of contribute to the damage of bridge infrastructure, or particularly the time-dependent deterioration. Now, if you look at bridges, the majority of the damage or deterioration happens primarily on the deck component. So we are focusing mostly on the deck, and the deck is where the rubber meets the road. That's where most of the damages happen, and that's where our focus of this research is. Now, typically, bridge decks are concrete because they're easy to cast or easy to put in place, and they're cheaper, much cheaper compared to other alternatives that might exist, and they can be put in any shape or form very easily. And that's why concrete decks are very common. Even if you have a concrete superstructure or a concrete girder or a steel girder, the deck would typically be a reinforced concrete or a reinforced concrete deck. But the problem with reinforced concrete deck is that they are also more susceptible to the damages that we talked about in the previous bullet point, the corrosion due to road salts, live load aberration like delamination, pitting, corrosion damage from the rebars and so on. And then weather effects also are more severe on concrete bridge decks. There's a picture on the lower bottom corner that shows you this is from a Federal Highway Technical Brief. It shows you that concrete bridge decks have got severe damages, and those are identified, and then they are patch filled and repaired and so on. In fact, currently there is testing going on in Rutgers BIST facility, which is quite well known. It's a large facility for testing full-size bridge decks up to 50 feet length, 25 feet wide, where we are seeing this kind of where we are doing accelerated deterioration testing under control environment, where we are simulating this bridge deck damage in concrete bridge decks of different types. So all of these, what happens is then in 20-25 years, you will be replacing the bridge deck every 20-25 years, and that causes traffic delay, diversions, traffic delay, maintenance, cost of operation, road users cost, all of those gets added, and then concrete decks do not come out to be very cost effective in general. But that's the majority of the deck that we see in this region or around the country. The other problem that we see with bridge decks is that with increasing truckload, or as the gross vehicle weight is getting increased, or the axle loads are getting increased also due to overweight trucks, or because of narrower tires that is used for efficiency and so on, they are increasing demands on structures, and the structures are aging, and as a result of that, their load rating or operational load rating is going down. So to increase the operational load rating, the dead load of the structure needs to be reduced so that they are becoming more efficient, and concrete decks are inherently heavier, and as a result of that, there is a need for lighter and efficient bridge deck that can address all these challenges. So with that background, we look at what are the options that we have. So the alternative automatically comes is the steel orthotropic bridge decks, which has been used quite intensively around the world, but mostly for long span signature bridges like suspension bridge or cable stay bridge. So the top right corner, you see the picture is of the Kirkenes Bridge in California during construction, where an orthotropic bridge deck is getting put in place. The lower bottom corner is the rehabilitation of, or the upper level deck replacement for Verrazano Narrows Bridge in New York City. This is also an orthotropic deck where the concrete fill grid deck is getting replaced by a steel orthotropic bridge deck. And the reason the designer went for a steel orthotropic bridge deck is that the concrete decks were not found to be cost effective or life cycle cost effective as a replacement. There were a lot of damages in the structures because of truck traffic and also because of the winter maintenance and all that we talked about. So orthotropic decks have got some advantages. They're lightweight, they're redundant, they're very structurally efficient. That means the load carrying capacity compared to the dead load is much higher. They're modular, so you can fabricate them very easily in a fabrication yard or some places. So for example, the Kirkenes Bridge, the deck was fabricated in Japan by a Japanese fabricator and was shipped to US. For Verrazano, the deck was fabricated in China and shipped to US. So this can be fabricated in a facility where, in a steel fabrication yard or facility where you can do all of that. And so they're very effective for accelerated construction. So for Verrazano, if you imagine, the bridge was never closed, only the lane closures were done overnight, and the deck replacement was made in 3 to 4 years' time. And then this is the only deck form that can provide a 100-year service life. Now, that is, I put a question mark there because some of us who make those kind of, who profess this kind of advantages, 100 years, nobody of us are going to survive to know whether the deck survived 100 years or not. But laboratory testing, accelerated testing, like fatigue testing and all that, shows that it is possible. Also, the corrosion in steel, unless it is very severely corroded environment, with the regular surface protection or coatings that we have, this can give you very easily a good service life. In fact, a repainting may be required every 35 or 40 years. So over the lifetime of the bridge, you might probably need to paint it twice. So overall, it gives you an improved life cycle performance and cost benefit. However, there are some deficiencies. For example, orthotropic decks, these are steel welded construction. They have a probability or propensity of fatigue cracking. In fact, early days when orthotropic decks were introduced initially in 1960s and then 70s and 80s, there has been a lot of fatigue cracking because for a couple of reasons. Number one, people were not aware of fatigue design for bridge structures or steel structures. So that was not in consideration. So a lot of these structures used to be very lightweight, very thin plates, and they were developing stresses that were not accounted for. The second problem was that people were not well accustomed to managing those stresses. So the details and the connections that were used, the connection details that were being used were not very efficient for those situations. But that problem has been somewhat resolved in modern construction because modern orthotropic decks are much more robust and much better fabricated, and fatigue design knowledge base has come in. So people are much more aware of how to manage those stresses and manage fatigue cracking and so on. The other issue that happens is wiring surface durability, because the wiring surface is now connected to a dissimilar material, the steel surface, and often there is a challenge of keeping them on the steel surface if there is not a proper bonding, and also the fatigue happens in the wiring surface because of flexibility of the deck plate. So that issue is also somewhat kind of addressed or resolved, but also at the same time that is something that needs to be paid attention to. But another important aspect is the high initial cost of fabrication, because if you have to be very careful with all the design and detailing for fatigue and other purposes, then the cost of fabrication goes high. And the initial cost of the deck is much higher compared to a concrete deck. And as a result of that, not many people are interested in going for orthotropic deck, thinking that we have to invest a lot, although the long-term savings might be much better. There is also a lack of rational design and fabrication standards or specifications. many designers go by their own design ideas and so on, and as a result of that, the specification tends to be or the fabrication and the design specifications tend to be over bloated or over designed or over prescriptive, and that kind of boosts up the cost because the labor costs are pretty high in US, and as a result of that, this does not become palatable for regular use. The most importantly is that if you want to use an orthotropic deck for the replacement of a concrete deck, traditional concrete deck, there is a big mismatch in the depth, because traditional concrete decks are typically 8 to 10 inches in thickness, whereas orthotropic decks are typically just the stiffener itself is about 12 inches, and then the overall, including floor beam and all that, might be much bigger. So as a result of that, there is a challenge with using orthotropic deck as a solution for the goal that we are having to address the challenge for the US bridge infrastructure by coming up with a lightweight and durable deck form. So over the years, there has been a development which is called, and a new type of deck has been proposed or thought of, is called corrugated core sandwich deck. So what happens is that if you look at the figure in the bottom left, where you see a typical orthotropic deck deformation profile of the deck slab under say a HL93 loading or ash to truck, what you see there is this deflection of the surface at most about 0.1 inch, right? However, there are some local distortion and local deformation because of the ribs. The ribs are twisting and bending, and as a result of that, the deck plate is also deforming in between the ribs. And you see that kind of a behavior typically in orthotropic decks. Now, what happens if we connect the orthotropic deck in the bottom? That means we have the bottom of the deck ribs now connected together with a plate. Then it kind of becomes a closed section, kind of a core in the middle. We can call it a corrugated core. And then the stiffness of the deck goes up. So I am showing on the right side a corrugated core a deck where you have a deck plate, you have a bottom plate, and you see the corrugation in between. And if we can build a deck like that, the stiffness goes up dramatically. So the left figure and the right figure, they're both to scale. So that means the depth of the orthotropic deck compared to the depth of the corrugated core deck, you can see the difference in deck thickness, where the deformation of the displacement of both the decks are pretty comparable, because both of them are about 0.1 inch displacement under HL93 or wheel loads or truck loads. So this is a very good option that can be used, and it's very lightweight. It's about 50 to 60 pounds per square foot, and we can use this kind of a deck to replace concrete deck. So we get the advantage of having better durability, long life, less chances of replacing them in the lifetime of the structure, and much better performance or much better addressing the challenges to the US bridge infrastructure. But this is not easy. The problem with corrugated core web is slightly different. This core concept is great, and it is not new. In fact, the very first one we see was done in NASA. Those days, NASA was not called NASA, it used to be called NACA. And Leibov and Hupka in 1951 came up with this deck concept for space structures or shuttles. And they were thinking if they can make something with this kind of form, because it's lightweight, it is stiff, and it can really carry a lot of weight. So whether they're very efficient, so whether they can use this kind of a deck concept for space structures. But the problem with that was the major challenge they faced, and that is still existing, is how you make this deck, how you build this deck. What's the process that you use to fabricate this deck? The challenge of this deck is that you have to make some connections between the core and the outer plates, and one of the plates cannot be fitted on the top. One of the plates cannot be done from inside, or connection between the core and the plate is a challenge. Leibov and Hupka thought about using rivets and bolts. Those days bolts did not exist. It was rivets or some kind of mechanical fasteners. But this was not very easy to do. It was a challenge. So 1951, coming down the road, there were probably some research done, but mostly the response and analysis of this kind of decks and so on. Then eventually, in right around mid-80s, there was a new welding process that came in called laser arc welding. And whether the laser arc welding came in, what it could do is it could do a lot of penetration and do much more effective fabrication. So now you can weld the deck from outside. And that is what you see here. I think the weld can be done from outside. So US Navy took up this process and they developed a deck which is called LASCOR. LASCOR is for laser corrugated deck. And significant money was spent and significant funding was used to develop this deck and research and all that. I think this deck work was done at Penn State's ARL. And then finally, this US Navy implemented that for USS Mount Whitney in 1994. But unfortunately, the cost of this fabricating these decks were enormous because of the laser technology was still in its infancy. The machine equipment cost a lot and so on. So this did not go anywhere and somehow fell through the cracks and fell out of favor. Now, let me give a little background about this laser welding. So this is what we are showing is a slight variation of what is called laser arc welding. Is called hybrid laser arc welding, where you can see in the left, this is an arm which has got the laser connected, and then there is another feeder that does traditional welding. So the laser is kind of pointed to the surface that is getting welded, and the right side, the figure shows that the laser is coming there. It's very hot. It's creating a keyhole through the material, and that is basically melting the material through. And then you are following up with a normal arc welding process, which is a gas metal arc welding, where this gas metal arc welding is now adding additional consumables or filler material to that weld. And as a result of that, you get a molten pool and a weld, which is very deep and through the thickness of the material. That's great because now you can do the welding from outside and penetrate to the thickness and have this process. So it's a hybrid process. It's not purely laser. It's laser plus traditional welding process like gas metal arc welding. And this gives you a much better welding weld result for this kind of construction. This also increases the deposition rate a lot. And this has been used quite successfully for thin plate construction, where a lot of ship structures have been used in modern times are getting built by this kind of techniques. This technique has been used to fabricate railway cars and others as well. The deposition rate is as high as 80 inch per minute and higher. So this is a very effective technique, but the process depends on the power of the laser. Now laser is getting cheaper and cheaper and powerful, more and more powerful. So nowadays 10, 15, 20 kilowatt lasers are easily available and they can be introduced, and Lincoln Electric has some of those capabilities and some of those equipment. So this laser technique is now becoming more commonplace and more easily available to the general for construction and using for thicker plates as well. Now, this concept of this corrugated core was first tried by FHWA under a IBRC grant, which is Innovative Bridge Research and Construction, I believe, grant. That was given to NJDOT and a company called PLS Systems and Applied Thermal Sciences. So they kind of collaborated along with University of Maine, and they wanted to use a corrugated deck concept for a replacement deck for this New Mills Bridge in Gardiner, Maine. So a lot of analysis work done at University of Maine. A small prototype was developed. You can see the picture on the top of a small prototype deck. But ultimately, somehow this project never came to fruition and never a full-scale deck was built. And if you look at the list of projects under IBRC grant, this remains as incomplete. In the meantime, as I said, shipbuilding industry and automobile industry and others were kind of trying to introduce this technique to do different kind of deck construction, corrugated or otherwise, and using hybrid laser arc welding for that process. Now, right around mid-2000s, there was some research done at Chalmers in Sweden, Chalmers University in Sweden, where they looked at whether they can use a corrugated deck for the bridge construction, right? So there were different conceptual designs were done, or conceptual analysis were done, a bunch of master's theses were done, and they did several finite element analysis and so on and so forth, and trying to see if analytically you can assess the fatigue performance of these joints and all that. And they typically looked at this hybrid laser arc welding process. Now in 2017 or timeframe, 2018 timeframe, they built a small prototype deck as well, which is, you can see this deck right over here, a corrugated deck, and they are using 2 hybrid laser arc weld bit to do the joint between the core and the deck plate, and then there is another one between the core and the bottom plate as well. So you can see these are the welds that they look like. So they're going through the top plate and getting into the bottom plate. So you can deposit the weld from outside. So that helps you to fabricate this deck. This kind of weld is also called a stack weld, like a nail. You're coming from outside and penetrating through. Now, where we come in, we started a research, and when we started this research, we were not aware of this Chalmers research so much. We kind of came up, we had an idea that IBRC grant was given by Federal Highway and nothing much had happened. So we kind of thought of doing this corrugated construction with a deck plate on the top and bottom, and try to see if we can use that in modern highway bridge construction with the requirements typical of orthotropic decks and so on and so forth. So we did some parametric work and some analysis and so on, and saw this is a very viable product and this is a very viable solution. Here I'm showing some finite element results. In the top bottom left, you see that this is the deck plate under the front wheel load. So if we cut a section through the front wheel on the deck plate, you can see the stresses. So there are stresses on the top of the plate and stresses on the bottom of the plate. So the blue line is the bottom of the top plate and red line is the top of the top plate. So you can see they're going just equal and opposite, kind of the same magnitude, but equal and opposite in sign kind of stress. So that tells you the deck plate is going through, primarily going through pure bending, not much of membrane stress, mostly bending stress. The same behavior you can see in the bottom plate, which is also shows this kind of pure bending kind of behavior because of the decks are kind of, it is going through, as you see under shear, the cores are kind of acting like truss. So they're transferring the loads right to the bottom plate. And then as a result of that, the section is kind of, you see this wavy deformation of the plate or the panel that you can see there. But this is much exaggerated view. Actually, you might not be able to see this wavy deformation at all. So this is typically what we saw the results. And we have a HBIR grant, which is now we are getting into the next phase. We just, we received the notification for funding and we are just signing the final agreement. So in the first phase of that, we tested a deck, very similar kind of a deck. You can see in our laboratory, we tested the fatigue testing of the deck done under simulated loading and so on. This is, as I am proud to inform, this is the kind of testing done first time at Rutgers Civil Lab, as I understand, because there was not this kind of equipment available. And I'm going to show you the equipment and the capabilities that we developed over the last year and a half, Rutgers under the funding from CATE and UTC to develop this kind of testing capabilities. So here is the deck testing picture. You see there is a 55 kV actuator coming from an overhead frame. And under the deck, you see some LVDTs that are measuring the displacements and so on. And inside the core, before we even completed the core, we put some gauges in there and that does some measurements and so on. And as all of these are coming to a data logger where we are connecting multiple channels and we are collecting data real time as fatigue test was done and static tests were done and so on and so forth. The problem is that this is an SBIR project, so there are some limitations on how much information we can divulge at this time because there are some proprietary information being developed. So as a result of that, we will not be able to share much more than what I'm showing now. But this is enough to show you that what's going on at Rutgers and what kind of work we are doing going forward. So this is our Rutgers Civil Engineering Laboratory. Some of you might have been here before and you have seen this civil lab. This red frame is kind of a fixture that is there in the lab for a long time. But we have also in the recent years have purchased these 3 actuators, a 110 kV actuator, a 55 kV actuator, and a 22 kV actuator. All are fatigue rated, having the capability to run fatigue tests at a very high number of frequencies and cycles. We have installed a new pump with a 30 gallon per minute flow capacity and so on, and some additional features and hydraulics in the lab, and a controller that can run at least 4 channels of testing simultaneously, and all kinds of testing that can be done. These are all MTS equipment. We purchased recently, as I said, from funding through UTC and Rutgers Skate, and this is something is now a new capability within the Rutgers civil lab to do this kind of testing. But we are also running with, we are not completely abandoning orthotropic decks. There are some other opportunities. Typically, orthotropic decks are closed rib that I did show you earlier, the picture. We also have a project on open rib orthotropic decks, with primarily the focus is to use these as short and medium span steel bridge structure. So here the concept you can see, the girders are made integral with the deck. So the whole assembly or the whole structure with the deck and the girder and floor beam all connected together will be brought to a bridge site and installed. Okay, so that's the goal. So if you have 2 girders, it's a stable configuration, so you can have another 2, and then you can have a joint in the tech slab and between the floor beams and so on, and then you can have a modular construction of bridge decks for short and medium span structure very quickly. And this is also very efficient. This has got less fabrication demands than the closed rib fabrication has, and as a result of that, this is a very viable option. So this is a project currently we are working on. We came up with some standard designs and all that. Right now we are getting ready to do a full-scale laboratory testing, and hopefully we will be able to share with you some of those in the next year's meeting or moving forward. So with that, I will just show you, this is the concept of the full-scale testing that we have, and we have now the capability to do that in our laboratory, and we will be going forward with this kind of testing very soon. So I will like to end my presentation with some acknowledgements. University Transportation Center Region 2 that funded some of the equipment and some of the project that I was showing you. The FHWA SBIR grant that's funded some of the projects, and also some of our own research that we did before. The work that I showed you is primarily Rutgers' own research, but nothing out of the SBIR project. Lincoln Electric, you saw the picture that I shared with you. Recently, I was at Lincoln Electric facility in Cleveland with their automation group and so on, where we are talking about how to go and implement this technique much more in steel bridge fabrication. AASHTO NSBA collaboration, TG16, there is a group that does collaborate, National Steel Bridge Alliance, along with AASHTO, and they have a group called Orthotropic Deck Panels. I'm the chair of this group. In fact, we just had our fall meeting this morning, and they are also very supportive of getting the steel decks as an alternative to concrete decks to be implemented for increasing the life cycle effectiveness of US bridge infrastructure. And there are a bunch of graduate students who helped me over the year to do these projects. Sophia Pastor, she was very much involved with the SBIR project, currently working with GPI. She did her master's project on this. Hyder Savman is a doctoral student working with me on several projects. Catherine Chen and Pai Sun did their master's project and thesis on some of the orthotropic deck stuff that I did show you. Undergraduate student Nicole Fredenreich, she worked on a summer internship with summer. And John Braley is an associate, Dr. John Braley is an associate with Rutgers Kate. He also helped with some of these projects, and of course Rutgers Kate for all the funding and the support over the years. With that, I have a list of references, and then finally, thank you for listening to my talk, and if you have any questions.
Thank you so much, Dr. Roy. We have a couple of questions in the chat pod. First, why aren't there more orthotropic decks built and designed in the United States, considering they're so popular around the world?
Why are those decks not fabricated, or?
Yeah, why are they so popular around the world, yet there's relatively few of them in the United States?
Yeah, so if you look at the history, and this is a very interesting question, because if you look at the history, US was ahead in orthotropic decks. So the very early orthotropic deck in North America was built in Vancouver, actually not, yes, in Vancouver, Portman Bridge, and then soon after the Poplar Street Bridge in Missouri, that was done in 1964 or 65, and following that up into 72 or 73, there were a series of bridges that were built in United States, mostly in California and Oregon and in that region. Then it kind of fell out of favor because of a couple of reasons. Number one, around that time, there were some concerns raised with the fatigue performance of orthotropic deck around the world because fatigue design provisions were coming into play. The second part is AWS and other specifications started coming in because of fatigue concerns, so they started getting a little more stringent. So cost of fabrication started going up. Third is people thought concrete deck is better than steel deck, so that's why they started going in that route for cost-effective purposes. But around the world, if you look at orthotropic decks are mostly used for signature bridge, which is typically the case nowadays in US as well. In any new signature bridge in recent times, like San Francisco Oakland Bay Bridge, the Carquinas, the Tacoma Narrows, the one of the redecking project I talked about, Verrazano Narrows, Trog's Neck is going on right now. Those are all orthotropic decks. Queensboro Bridge, it's an orthotropic deck currently getting redecked right now. So there are a lot of orthotropic deck that happens in US, which are all on signature structures. There are some work orthotropic deck used for movable bridges, like New Jersey DOT has its own, which is the Whitpen Bridge project. I was fortunate enough to be involved in that project. That's an orthotropic deck project. There are a few others in other part of the country as well. In around the world, the same situation. The long span bridges, the signature bridges has been orthotropic deck. Movable bridges has been orthotropic deck, but short and medium span market, people did not use orthotropic decks so much, probably because they are not probably cost viable. So the labor cost needs to go down, and that means you have to standardize them, have less control over the design process and all that, and let the fabricators decide what is the best performance that they can produce, or they will be doing performance-based solution. I think that will bring down the cost. There is a lot of interest going on. I mean, it is kind of really exciting times coming on orthotropic deck side.
Thank you. And you answered the next question there, which was why are short span bridges not used as often with orthotropic bridges? So we'll skip to the third question. What's the biggest challenge towards introducing this technology of corrugated panel decks in New Jersey? Is it cost, technical know-how, or agency buy-in?
Well, this will be agency buy-in because it is getting developed right now as a SBIR project, and the company which is involved is also someone in New Jersey. I cannot take the name because of they don't want to disclose that at this time. Once that gets kind of introduced and implemented, I think it would be agency buy-in. I think the next step would be and that is also a sequential process for SBIR process as well. We are in phase 2, and then probably it goes to phase 3, where New Jersey DOT might say, yes, we are interested to use one of those in our local environment and in our local roads or in some of the roads, and we try to see how it works out. So agency buy-in would be the concern. Cost, I don't think I do not know how the cost would come out. Definitely it will be costlier than concrete decks, but maybe not as costly as orthotropic decks because the process is different. There are some investment involved with building and all that. That is not in our scope. That is the company who does that. But eventually it would be probably agency buy-in.
Okay. And I see one final question. Does New Jersey offer any unique challenges, whether it's weather or traffic, towards the adoption of these kinds of bridges?
So New Jersey, New York is always in a very challenging environment. First of all, a lot of truck traffic and heavy loaded truck, overweight sometimes. And then we are in a cold environment where we consistently use road salt to keep our roads operable. So New Jersey is always, and then the seashore and all that. So the corrosion is also a concern. So New Jersey is in a very challenging environment for bridge decks or maintaining them in a good condition. Steel bridges are supposed to perform better. If you look at majority of the structures around the coastal area in New Jersey, within New Jersey port area and others, all of those major bridges are steel bridges because that used to be the material of choice at that time. But they performed well. Even in that environment, they performed well. The deck is the one that has been concrete, right? So we are now trying to change the deck also to steel. And the only thing is, if we can keep the wiring surface, and which I think we can, because wiring surfaces are also getting better, and we know how to do better integration with steel decks. It would be a very good solution to use, because first, it is lightweight. Second, fatigue concerns are much less in this corrugated construction. There are some other ways of building this corrugation also, or the deck also, which I did not touch upon in my presentation today. And then corrosion is not much of a problem, because either A, we can do these decks metallized or galvanized, the complete deck, or you can paint it. The deck is completely enclosed, so inside is kind of hermetically sealed. So outer surface is only the surface that can get affected, but then wiring surface is on the top. So corrosion concerns will be much, much less for these decks. So I think this has got a very big advantage or chances of success in New Jersey, New York area.
Okay, I believe that's it for the questions. Thank you again so much for the presentation.
Thank you for the opportunity.
And with that, we're going to move on to our third and final presentation. We're going to have two presenters here. First is Jani Gao, who is a Senior Research Associate at the C2 Smart Tier 1 University Transportation Center, funded by the US DOT. Jani completed her PhD in Transportation Planning and Engineering at NYU in 2020, and previously received her bachelor's degree in Science and Technology of Optical Information from Tongji University. Her research interests lie in data-driven and machine learning approach for transportation, emerging technologies including connected and autonomous vehicle applications, simulation modeling, and transportation economics. And presenting with her is Dr. Kaan Ozbay, currently a tenured professor of civil and urban engineering at NYU Tandon School of Engineering. He's also the director of the US DOT C2 Smart Center and was a professor at Rutgers University before joining NYU in 2013. Ozbay is a recipient of the prestigious National Science Foundation's Career Award. His research interests lie in transportation, covering a wide range of big data analytics for smart cities, simulation and modeling of large-scale complex transportation systems, feedback-based real-time traffic control, traffic safety, and applications of operations research techniques, and evacuation and humanitarian inventory control. Without further ado, go ahead.
Okay, thank you. Can you hear me?
We can hear you, yeah.
Yeah. I have to come up with a much shorter, like a one-liner about my bio, so it's just too much to listen to. Anyway, thank you for listening to us. This is, I was saying yesterday or 2 days ago that this is, I was surprised to hear that this is the 23rd research showcase. So I was obviously started my career at Rutgers, and obviously, we go back to the first research showcase. So it's been 23 years, so older than my son. So anyway, so this research, like Professor Roy did, even this research before us, this research has a lot of kind of history in it, especially from our perspective. So I'll give kind of a broad ideas, and then I'll let Jani Gao, who's a senior research scientist at C2 Smart, talk about the real stuff. So basically, life cycle cost analysis research, I had to check before my talk, 20 years ago when I was at Rutgers as an NJDOT project funded by Bureau of Research. And at that time, Dick Weed was the project manager. So we wrote a manual for life cycle cost analysis for NJDOT, which is still being cited and used. And then over time, this work kind of mushroomed to become something that we use to do additional work about the costs and different areas in transportation. So prior this work started as part of the NJDOT Bridge Research Program, one of the subtasks. We've been doing a lot of work with University of Mississippi Science and Technology, Missouri Science and Technology, funded by their UTC program. So a lot of the things that we use in this research project get their input from different projects at different times. So from the beginning, Jenny Gao, she was involved in this project. Professor Hani Nassif is the PI of the Bridge Research Program. Sami Demiroluk, who was my previous PhD student and stayed at Rutgers for a long time afterwards, was also active in this project. And Onur Kaan was a postdoc at C2 Smart at NYU, also was part of this project. So it's a group work, even as it is. And as I said, there's a lot of other people, other research involved in this. Just I have to acknowledge one thing. The original project that I mentioned that I did with my one of my past PhD students, Dima Jawad, our co-PI was Professor Neville Parker. So some of you might know Neville, who passed away a couple of weeks ago. It was a shock to all of us. He was a professor at City University of New York, UTRC, and it was one of the greatest experiences of my career to work with Neville Parker and do this work with Dick Weed as the project manager. So next slide, please. So basically, this, as I said, this project is about life cycle cost analysis and optimization for bridges, because this is part of the Bridge Resource Program. Of course, you could do this kind of analysis for other transportation infrastructure, and the current bridge software tool NJDOT has its capabilities of doing this, and it has many advanced functions. But like any other advanced software tool, it's not always very easy to use. And sometimes you want something a little bit simpler and quicker to use. The other thing is most of the this again very professional production level software tools, they're kind of black box, so they need to be kind of opened up a little bit and then studied more carefully. And that was also part of our task, like looking at different assumptions and functions and input that was part of the bridge resource management tool that the NJDOT is using. So basically, as a research team, we were trying to explore what's inside the current tool that NJDOT is using, kind of validating some of the assumptions and values, and then also looking to provide additional tools for the DOT to use in a more day-to-day basis and practical basis, and maybe try new ideas. So we do that in my main work in traffic simulation, for example. I mean, there's a very sophisticated simulation model, but if you want to go and change something within the model, it's impossible. So you do something a little bit simpler outside. Next slide, please. So basically, our approach. So we will focus on two aspects of this research. One is what we have done, and also kind of what we have in mind, and what can be done actually even further. So basically, we looked at the life cycle cost analysis formula, and this is again one thing. We looked at many things, but because here we're talking about life cycle cost analysis, we'll talk about the LCCF formula. We looked at the literature, and then proposed ways of improving the assumptions of the original formula and how we can improve that. Then while doing that, we came up with the idea of developing a spreadsheet-based, we call decision support tool, but evaluation tool for DOT to use on a day-to-day basis using the input from their bridge management software. So we're not creating reinventing the wheel. We are using the data and the input that they have already in their tool, but then trying to build a decision support tool and then very simple and easy to understand spreadsheet based for them to use, and then try to improve that based on its usage. So this was actually one of the outcomes of the project. And what I mean, as a researcher, what I understood is that sometimes this kind of an open, easy to evaluate tools using like a spreadsheet is very attractive because you can look at the equations, you can look at the data, you can make a small change, you can add another graph. So that was one of the ideas. Then of course you can take this to a level beyond what we have done, and this is kind of a future work. We kind of did some experiment during the fourth year of our project. Basically, use the web-based lifecycle cost analysis tool that we did as part of another research project with University of Missouri Science and Technology, and then maybe bring some of the optimization ideas to this project. So this is still at the kind of conceptual level, and we are doing a lot of things manually. But here the idea is basically use very fast and efficient genetic algorithms to find better scenarios to replace or repair bridges subject to some budget constraints and structural constraints. And again, even that part is because it's in-house programmed and developed. It's kind of open box. We know exactly what's inside, and we can explain what's happening. And this is actually Jenny's work. She's worked on that for the last several years. And what we showed that actually the genetic algorithm-based optimization solution that she implemented is very efficient and runs fast and actually has desirable features of, for example, not prioritizing only large bridges. So basically, when we looked at the DRM tool, it had this tendency of prioritizing big, large bridges because because of some utility functions they use inside. But here we can really customize that and pull some strings and then make sure that the recommended bridges are more diverse than just large bridges or very critical bridges and so on. So that gives us the flexibility of doing analysis, scenario analysis based on different criteria. So I'm going to stop here. So this is like the big picture, and I'm going to let Jenny just take you through the rest of the slides. I know we have a few 15 minutes, and then we'll take questions afterward. Thank you.
Thank you, Dr. Ozbay, and hello, everyone. My name is Jenny Gao. I'm a senior research associate at CITUSMART. As Dr. Ozbay just described, we adopt a kind of, we call it like multi-phase approach, and I'm going to introduce them one by one, starting from the small things that we changed towards, a more, I would say, like relatively complete tools that we develop. So the first step of this multi-phase approach is to kind of understand, the workflow of lifecycle cost analysis in the current bridge management software and investigate if there's a need to customize it to NJDOT specific needs. And what we did here is we perform a try and narrow based analysis for a selected bridge data set and found that, the default lifecycle cost analysis formula, utility formula, uses lifecycle cost over 2 times of the replacement cost as a part of the input. But what we found is once this LCC value exceed the 2 times of replacement cost, which means the utility of LCC becomes a negative value. And under that case, the utility value is not calculated by the existing tool. And this is not fully satisfactory in terms of DOT's needs. So based on these findings, we propose an alternative LCCA scaling formula to overcome this issue. And the new scaling formula, as you see on the bottom, it consider not only the replacement cost, but it kind of more towards a minimum maximum possible value that given lifecycle cost value given to that asset. And these estimated minimum and maximum values for the set are validated using the results obtained from the existing bridge management software. And this customized formulation becomes a part of the LCC Excel tool development that can be used to support decision making for DOT's bridge management. And the motivation behind this development of the Excel tool is really because the current software has pretty advanced LCC functions, but at the same time, these functions are complicated and require advanced agency-specific configuration and training to provide, to calculate the accurate result. And this may also take hours to run the analysis sometimes. So the main goal of this effort, mentioned by Dr. Ozbay previously, is to provide DOT with an easy to use and also an open source tool to improve their internal decision-making process regarding life cycle cost analysis of New Jersey bridges. This Excel tool is very easy to use. It allows users to easily modify all the parameters and policy rules from the building spreadsheet. It is much faster, I would say, take minutes instead of hours to run the analysis. And its best usage is to be used as a validation tool. So within this new Excel sheet-based tool, it provides new capability to the agency to be able to use it to test and validate new implementation ideas for life cycle cost analysis in a very quick and robust manner before these ideas are kind of incorporated into the current tool for final usage. So it's more like a testing and validation tool before you spend a whole bunch of time on the complete analysis. And the graph over here on the right shows the general flow chart of the spreadsheet tool. Both the MBI deterioration model and action benefit cost modulars are integrated into the tool, and it is capable of performing network level analysis. And benefits are triggered by the actions that is selected under given condition in both MBI National Bridge Inventory based and deferment based rules. And here I'm showing the input, output, and action log. And all of the input information is coming from current database or current practices that NJDOT is using. And these input information can be directly extracted from the existing bridge management software too. So no additional efforts needs to be made at this step. And outputs including what I mentioned before, the minimum, maximum LCC values of all possible combinations, LCC value of each individual bridge. Here we consider a period of 50 years and also the number and cost values of each action for the whole network calculated for each year. And this just showing very quickly visual example of the output of the LCCA Excel tool. And besides the customized formula and the spreadsheet-based tool, we also have a previous research, as Dr. Ozbay mentioned, a web-based LCCA tool called AssessMe LCCA. This tool is applicable to what has been discussed so far, but it has not been integrated with DOT's work yet. And this web-based tool is developed under the RECAST project called Research on Concrete Applications for Sustainable Transportation, led by the RECAST Tier 1 University Transportation Center based at Missouri University of Science and Technology. And the goal is really to provide an interactive LCCA tool that can quantify the cost of not only the conventional material, but also the new material and technology that can link, lab-based parameters to actual field performance. And this tool has been used for multiple projects already of RECAST and has been applied to novel materials like, ultra-high performance fiber reinforced concrete, crack-free HPC, fiber reinforcement, self-consolidating concrete for bridge decks and bridge beams. And this tool can automate the process of extracting network and access data from available database and interactively create LCC scenarios with customizable cost functions and performance functions. And the graphics on the right shows the graphic user interface of the web-based tool. And let me go to some of the highlights from this web-based tool. So first of all, it allows users to create multiple hypothetical and also real infrastructure LCC scenario. It can perform both deterministic analysis as well as probabilistic analysis that account for uncertainties. And these uncertainties are especially important for new materials that may have a higher uncertainty in terms of material cost, construction cost, and performance. It is highly interactive with various data visualization, analysis function, and also the reporting features. And this tool enables both the project level analysis and network level analysis. And it uses what we call a two-level bottom-up approach that supports multi-objective optimization. It also considers time effect, agency cost, and also accounts for user and social cost. And all of these cost components are optional, which means, if you only want to take a look at agency cost, there's an option there. And also, as I mentioned before, it provides stochastic treatment of the inherent uncertainties. So at the current version, we allowed up to, I think, 7 different parameters to be probabilistic, which means you can input not just a deterministic value, but also like a distribution, a triangle distribution, minimum maximum value, different formats of the parameters to account for the uncertainty. And for the project level 2, it first found project candidates. They're defined as all feasible maintenance rehabilitation strategy for each facility based on project level constraints. These constraints can be a facility's maximum traffic load or minimum acceptable serviceability. And then the associated cost of each project candidate is calculated. Then we can pass this value to the network level 2, which uses economic and engineering models with optimization algorithm to balance the trade-off between multiple objectives. And the ultimate goal here is to find the best combination of projects to meet network level goals. And the optimization algorithm, Dr. Ozbay touched a little bit on that we use is called NSGA, non-dominated sorting genetic algorithm to arrive at the optimal or near optimal life cycle strategy. And the core of this NSGA2 is the non-dominated sorting and also autonomous selection based on crowding distance. And of course, as one of the genetic algorithm, it uses crossover mutation to find the parallel optimal solution. And the reason why we picked this optimization algorithm is because NSGA has been proven to be one of the most efficient algorithms for multi-object optimization, that it can maintain population diversity at the same time of maintaining excellent individuals. And I'm not really going to the detailed equation, but just want to say that this network optimization problem can be formulated as a multi-choice, multi-dimensional knapsack problem. And here, just giving an example using like 2 objectives, we want to, of course, minimizing the total life cycle cost while considering, here in this example, considering the facility importance. And also for the network level constraints, of course, we're going to include budget limit. We also put one constraint to limit it to like 1 facility, 1 project candidate that, including the sequence of maintenance and rehabilitation actions, as well as this is a unique limits that we put called agency resource limitation, such as, the maximum number of bridges can be scheduled to be fixed at a given year. And very quickly to give some like visual representation of the output, this provides a glance at the project level output. On the left side are deterministic results, on the right side are probabilistic results. And it include cost project level output include cost breakdowns. And on the right top, this is the output with 2 objectives, and on the bottom, the 3D chart is the output like within 3 objectives. And as you can see over here, once you use probabilistic approach, the final result will be some kind of like distribution instead of like one deterministic value. And for the network level output, this is a little bit more complicated. It provides, So on the left, it provides the network level output, and on the right is how the final report looks like. And network level output contains all parallel optimal solutions. These are like equally good solutions. And what we do is we provide the selection probability, which indicate that how many times this solution, this optimum project set is selected as a Pareto optimal solution doing all probabilistic runs. So basically, the higher one are probably the better one, but there's also a trade-off within different objectives that the agency can actually filter. As you can see on the bottom, they can actually filter by rules, by their preference to pick the best solution that they would like to know. And just wrap up on what I've been talking about, we present a customized LCC scaling formula and the Excel tool for decision making. We also introduced this probabilistic LCCA-based framework, which is capable of dealing with new material or construction technologies, and also presents, probabilistic approach that are able to deal with the high level of uncertainty of novel material and construction technology. We kind of did a validation of the Sesame LCCA optimizer and compare with the results of the current, bridge management software used by DOT. And what we found is, based on the small scale and large scale tests, both of them kind of confirm that Sesame LCCA result in the selection of larger size bridges than the optimizer, and kind of like eliminate some of the small bridges. And the best thing that we found is it can utilize the total budget for the given study period, because there's a rollover budget function building with that. However, of course, this tool is not a production tool yet, and it requires customization and input data manipulation to be able to run different scenarios. So for the future work, we're thinking of combining it with the LCCA Excel tool, so we can build a preprocessor to make it easier to process data from the current bridge management software tool. And also, we're thinking of extend the Sesame LCCA to be able to run for multiple policies, because right now it runs only for policies such as deck rehabilitation. And with that, I want to thank NJDOT, because this work, especially the Excel-based lifecycle cost tool, cannot be done without their support. And also our partners at Rutgers Rhyme Lab, with all the help and great teamwork that we have been working together in the past few years. And with that, I will conclude our presentation and pass it back to Omid.
Thank you so much, Drs. Xiao and Ozbay. That was a wonderful presentation. At this time, we'll take questions. If anyone in the audience has questions, please use the question and answer pod. Currently, there are a few questions there already. First, how does the tool validate new implementation ideas before they are incorporated?
So let me just quickly say a few things, and Jenny can. So actually, the idea for the previous work was to about concrete that's used on bridges. So basically, there's some new concrete types of concrete that are not field tested, that are not that we don't have enough data. So we made an assumption that certain amount of improvement in terms of cracking or other load-related damage can be expected, but in a probabilistic way. So it's not just 5% increase, but in a probabilistic way. We also did that improvement based on what we see from a regular concrete, for example. So basically, it's an envelope. It's a lower level envelope that's a regular concrete, and then the improvement that's expected. So actually, this is kind of an idea borrowed from other fields where there's a new material. So basically, we are incorporating some of these ideas to kind of test the life cycle cost in terms of improvements. And of course, we have the cost information from the lab, or from even sometimes from the field in a limited manner from this new for this new material. So it's but the key here is that we're not saying just 2% improvement. We are just giving a probabilistic kind of idea, so that the improvement can be between this percent and that percent. So Jenny, if you want to add something to that.
Right. So I do believe this question might be, I know you were talking about Sesame LCCA, but I do believe this question might be asking about the Excel tool as well. So I'm going to just add a little bit detail around that part. And the reason why we can actually use, those lightweight spreadsheet for testing and validating implementation idea is really because I would say, like, instead of, getting all the information ready, putting into the existing bridge management tool and run it for hours to gather it out. And, like, once you change something, you have to re-put everything, you have to rerun it for another couple of hours. This lightweight tool is more kind of serve as you can pull all of the information from the existing bridge management tool, putting into the Excel sheet, and just get a quick sense of, what direction that this lifecycle cost analysis is telling you. And once an initial idea can be obtained from that, then we can put it back into the bridge management tool to get like more detailed analysis. But basically, this Excel tool allows you to do a very quick manipulation if there's anything you want to change, and if you realize that, oh, I want to test out with this policy rule rather than that policy rule, or I want to test out something specific, that allows you to make those quick changes.
So we gave you 2 answers for 1 question.
Thank you. And moving on, does this tool help determine localized repairs and improvements that can extend the life of a particular infrastructure component?
Jenny, you want to take on this?
I'm not sure if this is asking which tool, but
I will check on the speaker, but I think it came in during the second tool.
Yeah, I think the spreadsheet. So basically, again, that's the good thing about spreadsheet. It doesn't involve a lot of programming. So if you want to, for example, focus on local repairs and smaller improvements, you could do that. I mean, because it's just adding a few new equations. So that's the idea about the tool. So it's not like a big black box that you need to go and decipher the program, the 10,000 line program. So if you want to focus on these repairs, then you can kind of extend the tool or modify it very quickly. Right now, we are focusing on a few strategies that are borrowed from the BRM software. But if you want to add new strategies, it's very easily extendable to that.
Right, the tool is 100% open source, and it allows like overriding the functionality or like adding new policies, as Dr. Ozbay described.
Great, and we have one final question. That is, what social costs were considered in the decision-making process?
So the current one, we don't have. In the assessment one, we have social costs, but the spreadsheet tool is just basically regular cost. But you can add, for example, social cost as, and we tried all of that because we have a few other projects funded by NJDOT in the past. So we looked at all these social costs, like for example, cost of congestion, for example. So we can add that, and that congestion can be due to, for example, the length of the construction. If you're going to replace or repair a bridge. So we actually again tested some of these things very heavily. So we also added the cost of carbon emissions, related to construction and also related to congestion. So all these things are in the assessment tool, and they can be easily again incorporated into the spreadsheet because basically you have one cell that calculates the cost. So this is like a direct cost, and on top of it, you can add all these social costs, as I mentioned, very easily, and then have that. Unfortunately, one has to be careful when you add the social cost of congestion, for example. That tends to dominate everything else because there's so many cars and there's so much congestion, and then you have like average value of time that can become like completely much higher than any other cost in your cost function. So you need to weigh them. So there's a lot of ways of doing that, and actually a few papers on that. So great question. Thank you for asking.
Yeah, just add a little bit. So the congestion cost, just a clarification actually. The congestion cost Dr. Ozbay was talking about is actually, I think we categorize into user cost, but social cost in the assessment LCCA too. Of course, that include the carbon, the air pollution, but we also tested on like noise, if there's any monetary value that we can confirm that from, the noise reduction level as an improvement of the new material, that is also considered.
All right. Thank you so much. That is it for the questions, and that is it for the research showcase. Thank you, everybody, for joining us today. Thank you to all of our presenters, and thank you so much to our audience. Please remember when the presentation is over to fill out the survey, and we'll hopefully see everybody next year. Thank you.
Great. Thank you very much.
Bye. Thank you.
Excellent.